Now, welcome everyone. This is week 2, Trinity term 2021 of the Oxford Philosophy of Physics seminar. This week it's my very great pleasure to welcome Nora Mills-Boyd from Siena College in New York. Nora did her PhD in History and Philosophy of Science at the University of Pittsburgh before then. And somewhere in between, I believe, she was a research engineer at the Center for Experimental Nuclear Physics and Astrophysics at the University of Washington. And I'm assured that she is a fully trained forklift operator on top of all of that. She works on a number of things, including the complicated nature of empirical evidence. I think her most recent paper on that is Evidence Enriched in Philosophy of Science from 2018. But today she will be talking about laboratory astrophysics. And the question is laboratory astrophysics astrophysics?
Thank you, Adam. Thanks for inviting me to speak to you all. This is a real honor for me, so I appreciate it very much. Right, so is laboratory astrophysics astrophysics? Laboratory astrophysics sounds like an oxymoron. Reach for the stars as we might, we'll never bring them inside the terrestrial confines of our laboratories. So what on earth do physicists mean then when they tell us they are conducting laboratory astrophysics? Today, I'm going to argue that yes, terrestrial laboratory-based astrophysics is properly astrophysics, supposing the right sort of justifying arguments are securely in place. I'll also say something about the sort of limitations that researchers can encounter in their attempts to furnish such arguments. And throughout my talk today, I'm going to be focusing on empirical astrophysical research. So research in astrophysics involves many diverse methods, including modeling, calculation, simulation, pondering, and head scratching, which can all be done indoors. This is not the sense of laboratory astrophysics that I would be concerned with here. What I want to explore is the sense in which empirical astrophysical data can be produced from targets located within terrestrial laboratories. But first, I want to spend just a little bit of time talking about what makes astrophysics astrophysics in general, and the relationships it bears to astronomy and physics. Astronomy has concerned itself with the configuration, motion, and brightness of sources of light in the night sky. The simplicity of this way of framing the subject matter obscures the depth of the inquiry. It has been by learning from the configuration, motion, and brightness of sources of light in the night sky that human beings came to the view that we are not the center of our solar system, nor our galaxy, that there are other galaxies beyond our own, and so on. For a very long time in human history, a very important part of astronomy was cosmic cartography, mapping the light in the night sky, watching carefully for changes, and trying to build up a view of cosmic structure. For some, cosmic structure was presumed the most that we could hope to learn from astronomy. In a widely rehearsed passage, Comte prophesies that we would never get beyond the structure of the stars to know their nature and composition. He writes, we understand the possibility of determining their shapes, their distances, their sizes, and their movements, whereas we would never know how to study by any means their chemical composition or their mineralogical structure. Every notion of the true mean temperatures of the stars will necessarily always be concealed from us. The birth of astrophysics came with the application of physics to astronomy, in particular with the application of spectroscopy to light from the sun and then to the stars and nebulae. By comparing spectra thrown from astronomical sources with the spectra of elements committed to flame, arc, and spark in the laboratory, folks like Bunsen and Kirchhoff were able to match terrestrial sources with astronomical ones. And with this came the possibility of determining the presence of particular elements in astronomical bodies, shattering Comte's epistemic ceiling, and of determining the relative line of sight motions of such bodies. It would be a gross understatement to say that these advances were game changers. The new methods were so unfamiliar that the seats of power in the international astronomical community were still wary of the new astronomy around the turn of the century, and proponents of astronomical spectroscopy initially had to apply spectroscopy to the old cartographic approach to get traction in the worldwide astronomy community and with the titans of industry that funded it. Since those early days of astrophysics, the field has gained tremendous scope and new aims and projects have been embraced. Astrophysics still uses chemical composition and redshift for astronomical sources in their research, but also seek to understand the dynamical evolution of astronomical objects, processes and systems, and the physical mechanisms in play. They investigate the causes and evolution of supernovae and their remnants, the formation of stars, planets, and galaxies, the flow of energy and material, the interplay of plasma, gravity, magnetic fields, and so on. Still, in some ways, just like in the days of Bunsen and Kirchhoff, astrophysics is about understanding the application of physics to astronomical targets. In addition to receiving photons across the spectrum from astronomical sources, astrophysics research has also involved detecting more exotic messengers, including high-energy nuclei in the form of cosmic rays, neutrinos from the sun and supernovae, and gravitational radiation dissipated by merging astronomical bodies. There are also many terrestrial efforts to detect dark matter from our galactic halo in laboratory settings. Here, for instance, you see some philosophers of physics visiting the Axion dark matter experiment at the University of Washington's Center for Experimental Nuclear Physics and Astrophysics during a field trip from the PSA in 2018. Maybe you recognize some of these folks. ADMX, this experiment, aims to detect the signal of dark matter axions in a microwave cavity inside an 8 Tesla magnet under the floorboards here in the picture. So in addition to detecting messengers from space, empirical astrophysical research has also involved, for instance, attempts at producing dark matter candidates using terrestrial particle accelerators and accelerator-based nuclear astrophysics. So here again, you see the philosophers of physics learning about the University of Washington's tandem Van de Graaff accelerator, which is lurking behind engineer Doug Will in all its purple glory. And with such instruments, nuclear physicists can and have studied nuclear decay chains of astrophysical interest. So to take just one example, solar neutrinos are produced in a combination of different nuclear reactions in the sun, and each of these needs to be carefully characterized in order to compare predictions to data from solar neutrino detectors. Although they are quite rare, some of the highest energy solar neutrinos originate from the second forbidden beta decay of boron 8 into the ground state of beryllium 8. And nuclear physicists have studied the boron 8 decay spectrum using terrestrial accelerators, such as the one at University of Washington. So as we have seen, laboratory astrophysics comes in a couple flavors. Extending the reach of traditional detection of celestial light, terrestrial detectors have also been constructed to receive more exotic messengers. Laboratory astrophysics, even from its origins with astronomical spectroscopy, has also involved studying conditions relevant to physics in space in laboratory settings. For instance, by empirically investigating the spectra associated with different chemical elements and the spectra of decaying nuclei. Thus, laboratory astrophysics has proceeded by collecting messengers that physically travel from astronomical sources to us here on Earth, and by investigating instances of physical phenomena that occur in both on-world and off-world settings. And in light of all of these examples of laboratory astrophysics, I think it's useful to explicitly recognize that a certain pervasive premise about astrophysics in the philosophy of science is mistaken. So the pervasive yet mistaken premise is that astrophysics is a distinctly observational science, since its targets are too distant to experiment on. I'll just give you a few quotes here to illustrate instances of this premise in the philosophy of science literature on astrophysics. So for example, in a 2016 piece by Sybil Andrel, we have this quote: "Astrophysics and cosmology share a common problem in that they both need to acquire knowledge of their objects of research without directly interacting, manipulating, or constraining them." In a 2020 article, Melissa Jackert wrote, "Astrophysics faces methodological challenges as a result of being a predominantly observation-based science without access to traditional experiments." And in his delightful and outrageous paper from 1989, Ian Hacking scoffed, "Galactic experimentation is science fiction, while extragalactic experimentation is a bad joke." So it's interesting that this pervasive premise comes with a negative epistemic valence. For Andrel, the observation-limited nature of astrophysics is a problem. For Jackert, it's a challenge. The impression one gets is that philosophers think of astrophysicists as working with their hands tied. What they'd really like is experiment, but the targets of investigation are just too far away, and so they'll have to get by with looking and not touching. This view strikes me as doubly mistaken. First, it turns out that there is a sense in which there are laboratory-based astrophysics experiments after all. And second, even if there weren't, this wouldn't necessarily be a problem for acquiring astrophysical knowledge. This latter issue deserves another talk in its own right. So for now, I just want to stress that the very existence of laboratory astrophysics casts doubt on the common assumption that astrophysics, along with astronomy and cosmology, is a purely or distinctively observational science. So what makes astrophysics astrophysics is that it investigates the nature of celestial objects and processes using a suite of resources from physics. Laboratory astrophysics carries out such investigations using experiments on terrestrial targets. But how exactly? Are these scientists justified in representing their research as properly belonging to astrophysics and not just say laboratory physics from which one might draw astrophysical implications? So to get some purchase on these questions, I'm going to take us into the details of a particular laboratory astrophysics experiment so that we can investigate what's involved in practice and how it's all supposed to hang together. So in this section of the talk, I'm going to introduce the case, talk a bit about what makes data empirical in general, present a variety of ways in which the data from this particular experiment might be understood as empirical, and endorse one of these ways. And then I'll argue that if we want to make sense of the data in this particular case as both empirical and properly astrophysical, then it turns out that the conditions of the experiment in question undermine the aims of the experiment. I'll then summarize some upshots from the case and some takeaways for the epistemology of laboratory astrophysics. So I should say up front that I think this particular case is philosophically valuable because the premise of the experiment, that we can study supernovae by irradiating plastic in an earthly laboratory, is on its face peculiar enough to teach us something about what doing astrophysical research means to astrophysicists, and how far the research and practice strays from a purely or even characteristically observational science. This is what drew me to the case in the first place. But as I dug deeper into the details, I was surprised to find that the interpretation of the results of this research that the scientists themselves offer doesn't quite go through. So ultimately, I'll argue that this case also sheds light on epistemic challenges in laboratory astrophysics. So the particular laboratory-based astrophysics experiment that I want to consider was conducted at the National Ignition Facility at Lawrence Livermore National Laboratory, which uses a 4 megajoule laser facility to study matter in high energy density states, including, according to the NIF researchers, nucleosynthesis in stars and supernovae, instabilities in supernovae, opacity of stars, black hole accretion, nuclear reactions in stars and planetary interiors, in short, astrophysics. The data gathered from NIF experiments is clearly empirical with respect to some target. It's not, for instance, the result of a computer simulation alone, but is it really astrophysical empirical data? After all, the experiments at NIF are not performed by intervening on stars or other astrophysical systems themselves. Are the scientists just wrong to call such activities astrophysical experiments? Is this just a bad joke? For present purposes, I want to focus in on a particular paper from 2018. In this paper, the authors report results from a series of National Ignition Facility experiments first designed in 2009 that aim to study the Rayleigh-Taylor instability, which occurs at the boundaries between fluids of different densities, where the lower density fluid is somehow being pushed into the higher density one. This instability is thought to occur in supernovae at the interface between the forward shock moving outwards into the relatively low density circumstellar medium around the exploding star, and the induced reverse shock in the relatively high density expanding stellar ejecta. So the researchers wanted to investigate the possibility of high energy fluxes on the structure of the Rayleigh-Taylor instabilities in supernovae. In particular, they were interested in whether or not material would be removed from the interface between the two shocks in cases where the instability is evolving under high energy flux conditions. So at NIF, this massive laser system is focused on a tiny little holerum held in place at the tip of this point. And the lasers irradiating the holerum produce X-rays, which when absorbed by this little package depicted in gray, produce a blast wave through the relatively high density plastic into lower density foam. The experimenters report on 2 different conditions. There's a high flux case, which is depicted in the top right radiograph image of the physical experiment here, and a low flux case depicted in the bottom radiograph image. So notice that in the high flux case, the top image, there's no mushroom caps on the little RT fingers, and that the height of the region of mixed density is smaller than in the low flux case. So the researchers want to link this data from the X-ray blasted plastic and foam to astrophysical objects and processes, and to draw conclusions about the evolution of the RT instability in high flux astrophysical conditions. In service of this aim, they consider a particular supernova, SN 1993J, or they suspect that the RT instability would have been subjected to high fluxes. Model parameters fitted to empirical data from this supernova suggest that in a dimensionless sense, the energy fluxes present in the supernova would have been larger than those in the laboratory experiment. That is, the energy fluxes due to heat conducted from the shocked circumstellar medium back into the shocked stellar ejecta are evidently larger with respect to the astrophysical system than the fluxes present in the National Ignition Facility with respect to the experimental system. Insofar as the structure of the RT instability was affected in the experimental setup, the experimenters reason that the structure in the case of the supernova should have been affected too. Indeed, they suggest that insofar as the energy fluxes are larger in a dimensionless sense in the emergent supernova remnant than they are in the lab experiment, and the fluxes have a noticeable effect in the lab experiment, then the astrophysical fluxes seem likely to have a larger effect in the supernova remnant. They conclude realistic models of supernova remnants must account for the effects of thermal conduction to accurately predict their evolution at epochs immediately following the shock breakout. So the question I want to pose at this point is how should we construe the evidence generated by the National Ignition Facility experiment? Is this astrophysical evidence? Physical evidence from which one might make astrophysical inferences? How is it exactly that the conclusions about supernova remnants are supposed to have been drawn from terrestrial experiments? The short, but as we'll see, not quite satisfactory answer is that one can argue that the physics, the RT instabilities under the influence of high energy fluxes is the very same in both cases, such that in experimenting on X-ray blasted plastic and foam, researchers are probing the very same kind of physics playing out in far distant supernova. With this introduction to the experiment, let's ask, are the NIF empirical data astrophysical data? That is, are the radiograph images from the X-ray blasted plastic and foam empirical astrophysical data? So to answer this question, it'll be helpful to have a view of what makes data empirical in general. Elsewhere, I've argued that data, including astrophysical data, are empirical with respect to some target when there's an interpretation of the provenance of those data using the resources of an epistemic context, such that the data are products of causal interaction with the target. An epistemic context, in the sense I intend here, is just the collection of conceptual, theoretical, or representational resources from the perspective of which the data is to be interpreted. It is important to note that data are empirical relative to a target. So without specifying a target, it's impossible to say whether some particular data set is empirical or not. Data are also empirical relative to an epistemic context, and the epistemic context supplies the resources with which the data are interpreted. Data never speak for themselves, but rather always require interpretive resources, in particular background theory to furnish a causal story, connecting the worldly target of interest to the data collection and recording process. An important feature of the view of what makes data empirical that I'm defending is the causal production of data. And as I said, to be properly empirical, data should have been produced by causal processes that connect the worldly target of research to the processes of data collection and recording from the perspective of the epistemic context in which they're interpreted. There is no perspective outside of an epistemic context from which the causal processes can be identified and traced. Indeed, there's no perspective outside of an epistemic context from which the worldly target can be identified in the first place. Yet, using the resources of an epistemic context, it can be possible to answer the question, were these data produced by causal interaction with the target? This view of what makes data empirical obviously relies on the notion of causal interaction, which is a notoriously fraught notion for philosophers. I'm not committed to a special theory of causal interaction here. In fact, I believe that this view of what makes data empirical is probably compatible with a variety of ways of explicating the notion of causal interaction. And I think it's actually best that the precise explication of what counts as causal interaction be spelled out from within a particular epistemic context, using the resources of the particular background theory in play. So why is it important for their empirical character that data be connected by causal processes to worldly targets? To see why causal production matters, let's consider a characterization of what makes data empirical that eschews causal production and relies instead on ostension. And I'll suggest that this view suffers from a serious drawback. It's not easy to see how it could be applied to data sourced from far away worldly targets that no one can point to in an act of ostension. The characterization I want to consider comes from an insightful paper by Matthias Kaiser from 1991, titled From Rocks to Graphs, The Shaping of Phenomena. In this paper, Kaiser develops an abstract characterization of the epistemological structure that carries scientific reasoning from what he calls observable reality or data to empirical phenomena. The basic elements of an instance of the structure are an anchor point and inference tickets. Roughly, the anchor point is the bit of the world that sourced the data, and the inference tickets transform data by redescription and other operations licensed by theoretical resources, either via bootstrapping or the incorporation of accepted background theory, which might include incorporating data collected in other contexts. Although Kaiser goes on to formalize these intuitions, anchor points become zero structures and so on, the gist of the idea is as follows. The zero structure consists of the objects of scientific inquiry together with the simple act of presentation. My basic intuition here, says Kaiser, is that scientific data rest on raw material that can be presented or reproduced upon request. It is essential that this level is kept as simple as possible, e.g., this rock here, or these spots on the screen there, or in social science, these filled in questionnaires. The zero structure contains all those things that are to be subjected to scientific scrutiny, i.e. that are to be measured, weighed, radiated, diluted, accelerated, and so on. Thus, on Kaiser's view, what makes data empirical are these original and reproducible acts of ostension, like this rock here. As I hinted above, I believe that Kaiser's view is ill-suited to faraway targets in virtue of this feature of the account. On this account, when the material specimen is not present at hand, the scientist cannot anchor the data to it via acts of ostension like this rock here. Instead, on this account, the scientist is forced to anchor the data not to the worldly target of interest, but to some intermediary, as in these spots on the screen there. So let's consider an example of this sort. Here's a visualization of data from the Arecibo telescope, displaying spots that can be interpreted as radio signals from distant galaxies. On Kaiser's account, what makes the data visualized here empirical is that they can be picked out by ostension, by some scientist gesturing to the image, these spots on the screen here. This approach locates the empirical at the site where some bit of the world is present to the perception of a human inquirer. In this case, the spots on the image are what is present to the inquirer. But this approach seems to miss the point. The data displayed here are empirical data with respect to galaxies. They are data encoding the radio frequency emissions of galaxies over time in virtue of being produced by the interaction of electromagnetic radiation emitted by those galaxies traveling through space and interacting with the receiver of the Arecibo Observatory's telescope, and subsequently the rest of the readout apparatus of the telescope. So taking my view of what makes data empirical on board, let's return to the National Ignition Facility Rayleigh-Taylor hydrodynamic instability experiment. How should we construe the data generated by the National Ignition Facility experiment? Are these empirical astrophysical data? Following my view, we should ask first, what is the worldly target of the National Ignition Facility research? And second, by causal interaction with what has the data been produced from the perspective of the relevant epistemic context? Perhaps we should say that the worldly target is supernova 1993J. Yet the causal interaction producing the experimental data is with the NIF plastic and foam, thereby ruining the empirical nature of the data with respect to the astrophysical target. Or perhaps we should say that the NIF plastic and foam targets are the worldly targets of research too, but that would ruin the astrophysical nature of the data. To recover a sense in which this experiment produces astrophysical data, we could construe the worldly target as the general class of RT hydrodynamic instabilities in high energy density states of matter. Then, insofar as laboratory systems and far removed astrophysical ones instantiate this very same physics, investigating the effect of high energy fluxes on hydrodynamic instabilities in laboratory plastic and foam is just to investigate the very physics playing out in astrophysical contexts. NIF data are empirical with respect to high energy density states of matter and their behavior, since there is an interpretation of the provenance of those data such that they are the products of causal interaction of the matter energized and confined by the NIF lasers with the laboratory detector systems. Insofar as such high energy density states are instantiated in faraway astrophysical systems too, the data gathered in the NIF experiments can be used to constrain astrophysical theorizing. So we should like to know, what is the justification for thinking that the same physics is instantiated in both contexts? As I've already alluded, the NIF researchers appeal to the hydrodynamic similarity of the two contexts. Indeed, the authors of the NIF article that I've been referring to appeal to a well-cited paper by Rayleigh-Taylor et al. From 1999 that lays out particular criteria for establishing the physical similarity between laboratory conditions and those occurring naturally in supernova hydrodynamics. Hydrodynamical systems, well described by the Euler equations, can exist at vastly different scales. Rayleigh-Taylor et al. Argued that as long as these conditions are met, that is, viscosity and thermal conductivity are negligible, the energy density per unit volume of the fluid is proportional to pressure, dynamic influence of magnetic fields is absent, and the initial conditions are geometrically similar, the hydrodynamic behavior of the systems will be the same. Rayleigh-Taylor et al. Go so far as to state that if those similarity conditions are satisfied in the experimental and natural systems, then the two systems are identical with respect to their hydrodynamic physics. In particular, a laboratory system meeting these conditions should exhibit identical hydrodynamic behavior to an astrophysical system that also meets these conditions and has the same value of a dimensionless parameter that they call the Euler number. The NIF researchers, actually Rayleigh-Taylor calls it the Euler number, the NIF researchers call it the Rayleigh-Taylor number, and engineers call like 1 over that squared the Euler number. So, and none of this is to be confused with Euler's number. But this particular dimensionless parameter, they argue, should have the same, this particular parameter should have the same value for hydrodynamic similarity to obtain in these contexts. And this parameter could be interpreted as the ratio between pressure forces and inertial forces associated with a hydrodynamic system. So the similarity can break down, however, when energy flow by particle heat conduction or energy flow by radiation flux are non-negligible. Rayleigh-Taylor et al. Cautioned that the limit of applicability of this similarity is set by the validity of Euler's equations as an adequate description of the hydrodynamics. So if the argument from hydrodynamic similarity requires that the energy flux from heat conduction in the systems be negligible, but the experiment in question is designed to investigate how high energy flux from heat conduction influences the structure and evolution of the hydrodynamic instability, does the very aim of the experiment undercut the specified connection to astrophysical targets, like supernova 1993J? To satisfy this worry, we should like to know more about specifically what the criteria regarding heat conduction and radiation flux that need to be met are, and then to check whether or not, in fact, those criteria are fulfilled in this context. So following Rayleigh-Taylor et al., the criterion regarding heat conduction is that the convective transport needs to dominate conduction in the systems of interest. Regarding radiation flux, convective transport ought to dominate the radiation contribution to thermal diffusivity. Or they write, in cases where it's inconvenient to determine this due to difficulties evaluating the mean free path of photons, it's sufficient to show that the lower limit of the radiation cooling time is much larger than the characteristic hydrodynamic time. So armed with these details, we can ask, do these conditions obtain in the systems of interest in the NIF experiment and the astrophysical one? From what I gather, these conditions are in fact not met. As the authors explain, for the supernova, the interface between the shocked ejecta and the shocked circumstellar medium thus arises hydrodynamically, and the transition across it will initially occur in a few ion-ion mean-free paths. Because pressure is continuous across such an interface, the temperature is much higher in the shocked, less dense circumstellar medium than in the denser ejecta. This leads to the possibility of radiative or conductive transport of energy into the denser ejecta, which in turn can affect the evolution of the Rayleigh-Taylor instability at the interface by ablating material from it. In addition, there is a phase when the radiation from matter heated by the reverse shock might also affect the RT. In particular, they state that pure hydrodynamics may well be insufficient to accurately predict the structure of the young supernova remnant, and that regarding heat conduction, as the shock structure at the interface between the circumstellar medium and the dense ejecta forms, heat flow is possible by radiation and electron heat conduction. The radiative losses from the shocked layer produced by the reverse shock are found to be large enough to cool it significantly. The energy flux associated with the cooling is much, much greater than the mechanical energy flux for a period of time, showing that the hydrodynamic model is not sufficient to accurately describe the behavior. Indeed, the authors state that the incoming flux, energy flux by heat conduction is larger than the incoming mechanical energy flux by a factor of 1,000 at all times, and reason that this flux by heat conduction is large enough that this energy flux may be a dominant effect in establishing the structure of the layer. We can see this failure to meet the necessary similarity conditions fairly directly here in this table comparing select dimensionless parameters from the laboratory and astrophysical systems. For instance, consider the energy flux ratio R, which has the radiative energy flux in the numerator and the mechanical energy flux in the denominator. For the similarity conditions to be met, the denominator would have to swamp the numerator. Yet for R in supernova, we have a value of 10 to the 3. So note also that the Euler or Ryukyov numbers for the two systems are not the same. On this latter point, the researchers explain that while physical similarity between systems does not require the identity of all dimensionless parameters, Ryukyov et al.'s argument does require that the Euler-Ryukyov number be the same for the systems whose similarity is to be established. In this case, the authors note that the Euler-Ryukyov number for these two systems differ according to best estimates, but that the assumptions upon which those estimates have been made could vary by at least an order of magnitude. And in response to these circumstances, they clarify in a supplementary note to the primary publication that the main goal of the work is not to scale their laboratory results to a specific astrophysical object, such as supernova 1993J, but rather to show the importance of energy fluxes in the evolution of young supernova remnants more generally. So here's the argument that I think these authors would need to make regarding the astrophysical relevance of these NIF experiments. Drawing on Rayleigh-Taylor et al., they suppose that in general, hydrodynamic systems that meet Rayleigh-Taylor similarity criteria and have the same Euler-Ryukyov number will exhibit the same hydrodynamic phenomena. Therefore, in particular, if the laboratory system and astrophysical systems of interest meet Rayleigh-Taylor similarity criteria and have the same Euler-Ryukyov number, then they will exhibit the same hydrodynamic phenomena. It then needs to be established that the laboratory system and the astrophysical system of interest, in fact, meet the criteria and have the same Euler-Ryukyov number. Then, supposing the NIF experiments show that the laboratory system displays a particular hydrodynamic phenomenon, the astrophysical system can be expected to display the same phenomenon too. However, the problem is that the similarity argument evidently fails in this case, since it's not the case that the laboratory system and the astrophysical one meet the criteria and share the same Euler-Ryukyov number. Instead, neither the laboratory system nor the astrophysical system of interest meet the necessary criteria, and these systems have different Euler-Ryukyov numbers. Therefore, while the experiments demonstrate that high flux conditions do influence the structure of the RT instability in the laboratory conditions, the argument for astrophysical relevance seems incomplete. What can be gleaned from this case? What did we learn from these experiments? It seems clear that modeling these systems as evolving hydrodynamically is not appropriate. And therefore, we do not have good reasons to suspect that the usual mushroom-shaped Rayleigh-Taylor instability fingers will show up in the supernova remnants with high energy flux conditions. Expecting such structures in supernova remnants was premised on hydrodynamic modeling, but we've seen that the high flux conditions make such modeling inappropriate. But this much might already have been clear before the NIF experiments on plastic and foam were even performed. That is reason to doubt the applicability of the usual hydrodynamic evolution of the RT instability in supernova remnants where high energy flux conditions are present could have been gleaned already from the conditions and arguments set out in Rayleigh-Taylor et al. Combining these arguments with empirical data from supernova 1993J supporting the presence of high energy flux would have already been enough to cast doubt on the evolution of the structure of the RT fingers in the resulting supernova remnant. If the final epistemic payoff of the NIF experiment is supposed to be the relatively modest point that caution is warranted regarding predictions and interpretations of RT-like structures in supernova remnants in high energy flux conditions, then it's not clear that the experiment on plastic and foam adds anything new. One might consider the epistemic payoff as rather the demonstration that ablation of material from the RT fingers occurs in the experimental conditions. That's all well and good, but again, that doesn't itself speak to the astrophysical systems. Nevertheless, the authors in some passages seem to advance an epistemic payoff that goes beyond the modest point. They seem to argue that since the conditions that are possible for the demonstrated phenomena of interest in the laboratory setting are, in a dimensional sense, larger in the astrophysical system, that ought to give us reason to expect the phenomenon in the astrophysical system as well, and the effect, and that the effect would indeed be larger in the astrophysical system. Is this argument convincing? It seems to me not, since the success of the argument depends on the soundness of the similarity argument, which in this case has evidently failed. Okay, so let's look at some of the upshots from this case. First, laboratory astrophysics is not an oxymoron. I've argued that empirical astrophysical data must derive from a causal chain that has one end anchored in the worldly target of interest. In astrophysics, that doesn't necessarily mean that the target has to be outside of terrestrial laboratories. Powerful similarity arguments are available to cast laboratory targets in far removed astrophysical ones as instantiating identical physics. Insofar as phenomena that are identical with respect to the relevant physics can occur in laboratory conditions, then physics that occurs in astrophysical systems as well as laboratory ones can be studied on Earth. So laboratory astrophysics teaches us about astrophysics by teaching us about kinds of physical phenomena that occur in laboratories and in astrophysical systems too. Laboratory astrophysics teaches us astrophysics by teaching us physics. These arguments can break down when the necessary conditions do not obtain. If the relevant conditions in the laboratory and astrophysical targets are not the same, then the crucial epistemic link will be broken. In such cases, other arguments would have to be furnished in order to justify couching data derived from terrestrial targets as empirical astrophysical data. If such arguments cannot be made, then the research may still be construed as yielding empirical data, just not empirical astrophysical data. Of course, then that doesn't mean that astrophysicists couldn't then learn about these astrophysical targets using other methods. So citing examples of laboratory astrophysics, I've argued that this pervasive premise, according to which astrophysics is a distinctly observational science, since its targets are too distant to experiment on, is mistaken. Some empirical astrophysics evidence comes from producing relevant conditions in the laboratory. Does this mean that astrophysicists can do their research from the laboratory alone without appealing to traditional astronomical data produced by celestial messengers? Is or astrophysics the new armchair ornithology? This is not what I mean to suggest. So let me be clear. The epistemic successes of laboratory research in astrophysics depend on several key arguments that underwrite ascribing the same physics to laboratory and celestial targets. There will have to be some overarching similarity argument according to which the same physics suitably described could be instantiated in both targets. Such an argument will come with limitations and conditions under which it will not hold. Arguments also need to be made that appropriate conditions for the similarity argument to hold do in fact obtain in both the laboratory and celestial targets. Good arguments that the relevant conditions obtain in the celestial regime are furnished by the astronomical messengers. Laboratory astrophysics could not thrive without auxiliary empirical evidence from celestial sources that constrain theorizing about those sources and guidance about which models can be appropriately applied to them. That is, laboratory astrophysics relies in important part on astronomical messengers to drive the relevant similarity arguments. While the sort of similarity arguments that can be made for hydrodynamic systems are particularly powerful if you can get them to go through, the basic epistemological issue here is utterly ubiquitous in scientific research. The general issue is that of external validity. In much empirical research, arguing for external validity involves addressing features or conditions of the proximal and ultimate research target that could plausibly make a relevant difference. No two targets or experiments are identical in all respects. This fact is irrelevant to the epistemology of science in practice. In practice, scientists must concern themselves with discerning, to the best of their abilities, features and conditions that might make a relevant difference, and then either providing arguments that the differences may be ignored for the limited purposes at hand, concocting circumstances so that the differences become negligible, or else modifying the way they conceive of the scope of their research so as to responsibly accommodate those differences. Without such measures, the threat of tragically local data looms large, to use Latour's phrase. Without characterizing research targets as belonging to a type, we would be locked into an insufferably parochial epistemology. Avoiding tragically local data can involve strategic characterization of the research target and good arguments backed by good auxiliary evidence to support that characterization. Today, I've highlighted a certain kind of similarity argument that can be made for some hydrodynamic systems There are, of course, other types of arguments that can be made in other contexts. External validity claims need to be justified. They may be challenged by those clever enough to come up with physically plausible difference makers that have not yet been taken into account, or by surprising empirical results. In general, scientists do well to take opportunities to empirically test their external validity arguments, and indeed to rigorously seek out such opportunities. This strikes me as a crucial aspect of the epistemology of experiment in general. It's part of what's involved in arguing for the epistemic significance of a result, and in particular, a part of what is involved in eliminating candidate sources of error, confusion, and alternative explanations. While in some cases it may be methodologically prudent to assume external validity without having yet done due diligence to conceive of cogent arguments for those claims and thoroughly hunted for defeaters, just as a way to get things started, scientists, ought not be satisfied with such a situation long if they can help it. If they can help it. So I like to think about this in terms of what I've elsewhere called enriched lines of evidence. The idea is that the epistemic utility of some empirical result depends on the details of its provenance. To use an empirical result in an epistemically responsible way, one has to know quite a bit about what assumptions have been baked into it. Some of those assumptions will cause epistemic problems for certain applications, for instance, in constraining a particular hypothesis or in attempting to combine the result with others that were generated by incorporating different assumptions. On this view, supplying good arguments for external validity involves arguing that the assumptions baked into a particular empirical result won't cause epistemic problems for the intended application. So with all of this in mind, I'd like to offer my own brief take on a recent disagreement around the epistemology of analog experiments in connection with Hawking radiation in the philosophy of science literature. So I'm going out on a bit of a limb here, and I'm sure I'll hear about it in the Q&A. But from what I gather, the case against interpreting the results of analog experiments as confirming the existence of Hawking radiation for astrophysical black holes, as raised by Crowther, Linneman, and Vutrick, is the following. A successful argument for confirmation would have to establish that both an astrophysical black hole and the laboratory analog are appropriately modeled by the relevant semi-classical model and analog model, respectively. Whether or not the semi-classical model is appropriate for the astrophysical black hole depends on whether certain conditions obtain in such physical systems, but that those conditions do in fact obtain has not yet been shown. Therefore, the behavior of the analog system does not give us good grounds to expect the relevantly similar behavior in the astrophysical system, because there are pressing open questions about the applicability of the relevant model to the astrophysical system. Crowther, Linneman, and Vutrick suggest that good reasons to think that the model is appropriate may come in the future, perhaps with better theoretical understanding of quantum gravity, or with empirical results supporting the existence of Hawking radiation from small black holes directly. But they argue that without better arguments supporting the physical adequacy of the semi-classical model to astrophysical black holes, results from analog experiments cannot get us all the way to confirmation of astrophysical Hawking radiation. So my hot take here is that the relevant questions are, first, what is the argument that the semi-classical model is appropriate for modeling an astrophysical black hole in this epistemic context? You could just assume that this model is applicable, but that would saddle you with a kind of epistemic debt. The epistemic significance of the experimental results would then be, if the semi-classical model happens to apply to astrophysical black holes, then the analog experiment results yields reason to expect Hawking radiation from astrophysical systems too. It would be more satisfying to have some further arguments to support the assumption that the modeling decision is appropriate in this context. In a 2020 paper, Evans and Thibault suggests that the case from analog experiments could be strengthened by stronger universality arguments and a new generation of analog experiments showing Hawking radiation in diverse media. However, this assessment seems to leave out what Crowther, Linneman, and Vutrick were calling for, namely arguments that astrophysical black holes have the right sort of features to be appropriately modeled by the semi-classical models that would connect them via the universality arguments to the analog systems. If Evans and Thibault envision the relevant future evidence to come from experiments on diverse media other than astrophysical black holes, then it would still seem that an important piece of the arguments would be missing. Even if physically adequate models of many other systems can be convincingly shown to belong to the same universality class as the analog systems of the experiments already performed, this would not demonstrate that the astrophysical black holes are appropriately modeled by the relevant semi-classical model. So to me, this does seem like a crucial part of the overall argument for expecting Hawking radiation in astrophysical black holes on the basis of analog laboratory phenomena. So the second key question is whether good arguments for the appropriateness of the semi-classical model can be generated. So to conclude, let's circle back to the question that we began with. Is laboratory astrophysics astrophysics? I've characterized astrophysical research as involving the investigation of the nature of celestial phenomena using a suite of resources from physics. I've discussed some examples of laboratory astrophysics in which the relevantly same physics is studied in laboratory settings, such as accelerator-based nuclear astrophysics experiments. Laboratory targets can instantiate the same physics as astrophysical targets under the right description and with the right arguments. I discussed a case in which it may have first seemed that powerful similarity arguments could be made to justify understanding the Rayleigh-Taylor instability in laboratory plastic and foam in the distant supernovae as instantiating the same physics. However, it turned out that the particular experiment that was the subject of my case study, it turned out that the aims of the experiment, namely to study the evolution of this instability under high energy flux conditions, undermined the needed similarity argument. So my answer to this guiding question is a qualified yes. Under the right conditions, laboratory astrophysics is astrophysics.